Hey guys, gals, anyone who's joining in today. First of all, we appreciate your time. Thanks for being here. Dan introduced himself. Some of you may know me, some of you might not. My name is Eric Brooks. I've been with Q-SYS for about a year now, and I come by way of higher education. So I worked for Virginia Tech prior to joining Q-SYS I was there for about 8 years, doing AV integration, audio engineering, things of that nature. Prior to that, worked for an integrator in South Carolina. We did, daytime integration and then production by night. So I had no life. So I was happy to go to the higher education sphere and do all that. So I'm sure a lot of you guys understand. But anyways, without further ado, again, thanks for joining today. Dan addressed the chat. If you have any questions, feel free to post those. We'll answer them live or, in the chat itself. So if we get through this content in the next hour or so, we're going to have some time for Q&A at the very end. So, if you have any questions as it arises, feel free. You can wait for that too. So with that being said, I do we have a good amount of content to go through. So we're going to start kind of rolling here. So basically today, what we're going to be discussing is kind of demystifying and talking about some best practices when it comes to, game structure and AEC in Q-SYS specifically, but also kind of holistically, when it comes to just best practices. So what we're going to do is we're going to take a deep dive into some of these topics, game structure, AEC, a little bit of troubleshooting, kind of really how to help optimize your system really the best way possible. Some of these issues we see our team gets calls, so we're going to hopefully help you address some of those. And if there's something we don't talk about today, feel free to ping your local solutions architect like myself, your applications engineer. We'd be happy to go further into the weeds with you. So anyways, let's get cranking here. So cool. First, hopefully you all can see this. Let me make sure I'm getting this out of the way here. Okay, cool. So essentially what we're going to do is we are going to more or less walk through kind of signal flow, right? So we are essentially going to start with our input section, address gain staging. We're going to go through some filtering and processing, talk about user program levels, best practices surrounding that. Also looking at some, mixers, some automatic mixers, standard mixers, how to appropriately set those, output signal conditioning, and then finally our audio output to our downstream devices. So with that being said, 10,000 foot view, we're going to start on this side, work to the right, obviously signal flow. But what we need to do is essentially really prioritize and spend some time talking about healthy gain into our system for best results, right? So essentially, this is the crucial part of any audio system. We want to make sure that we are getting the correct input unity gain so that we can optimize our system. And trust me, this really helps with any AEC best practices. This kind of helps. This is the glue that kind of keeps everything together in the system. And you'd be surprised how often we kind of have to go through this. So hopefully today we can really rock and roll and just kind of get into the weeds of it. But high level, garbage in equals garbage out. Keep that in mind as we go through the system. We want to make sure that we are getting that optimal input gain level. So with that being said, let's kind of dive in and start to work through some of this here. All right, so let's take a second to kind of talk about the language of audio, essentially what these terms stand for, what they mean, and how they apply to audio in general and Q-SYS. So essentially, we're going to start off with dBu, right? So what is dBu? So dBu is decibels, and then the U stands for decibels unloaded. So historically, with audio systems circuits, they were based on a 600 ohm impedance. So in those systems, 1 milliwatt of power required 0.775 volts. Ohm's law, power times resistance equals voltage squared. So that's where that comes from. This is a base 10 logarithmic reference for signal level, comparing how loud a signal is measured against that 0.775 reference voltage. So just keep that in mind as we go through. Looking down here at our noise floor, every analog device has an inherent electrical noise when it's powered on and that circuit is energized. So for Q-SYS, essentially our maximum noise floor is approximately negative 81 dBu for most of our device specs. Looking at the top here, our clipping point, this is the maximum input level before distortion occurs in the system. And the clipping level is essentially having an input voltage higher than the maximum voltage of the power supply itself, or if the incoming signal's sine wave is larger than the input device can process, the excess sine wave gets clipped down or distorted. It's overdriven to fit into that. So it's pretty audible. We've all heard it. Everyone, I feel like, understands what that clipping point is, distortion, essentially. So dynamic range, this is going to be the usable range between the noise floor and the clipping point itself. So dynamic range essentially tells us how much clean signal we have to work with before the signal is either buried in noise or is pushed into distortion, right? So for Q-SYS, we specify that dynamic range at roughly 105 dB. And again, if you see dB alone, it's essentially a logarithmic relational value comparing 2 points. So if you like see dB without the A, the C, or the U acronym at the end of it, just remember that's a relational value. Okay, so high level, really quick before we move on, essentially, gain structure is about managing the space between the quietest usable signal and the loudest signal a device can handle. The noise floor is the bottom of that range, clipping is the top, and your dynamic range is that usable space in between. So the goal is to essentially make sure you have strong enough signal to stay above the noise floor, but not so hot that it clips or creates distortion in our system. Cool. So looking at this chart here, this is more or less the same chart, but it's broken down a bit further. So what we're looking at is a properly set gain structure keeps the signal well above the noise floor while leaving enough headroom to avoid clipping again. And we want the signal level to be significantly above that noise floor. Otherwise, it won't sound very good. The sweet spot is discernible audio, but it kind of also allows for volume fluctuations without clipping. So it allows for peaks, spikes, transient, level adjustments in the system itself. So with that being said, our target level, in the analog side is +4 dBu, right? So that is the normal operating level for the signal. At professional line level, this is typically, +4 dBu. For consumer line level, this is typically -10 dBV, which translates to about -7.8 dBu. For dynamic microphones, they're much lower, often around 60 -60 dBV, and that translates to about -57.8 dBu. For condenser mics, there's really not a standard. They kind of vary per microphone itself, so just something to keep in mind. And then, so here we're looking at our headroom, and the headroom is the space above that nominal level before it clips. So essentially the top 20 dBu gives room for those value changes, signal peaks, signal spikes. And then, keep in mind that with SPL, +10 dB is perceived as 2 times as loud logarithmically. Signal to noise ratio, also known as SNR, that is essentially the difference between the nominal level and the noise floor itself. So here we have about 85 dBu of SNR in the system. And the higher the SNR means a cleaner signal with more tolerance for adjustments. So moving down the line here, next we're going to look kind of at our preamp circuits. So the analog preamp gain sets the signal level to unity before the conversion to digital. So all DSPs make use of analog preamp circuitry. The input device here is the physical microphone that creates the original analog voltage signal. Your analog preamp, essentially the gain that is added to bring the mic signal up to that desired nominal level before the A to D conversion. Analog to digital converter, A to D conversion, that is essentially the analog waveform is sampled and converted into digital values that represent the amplitude over time. So here, it's very important to note that clean conversion matters. So if the signal clips or is too noisy before the conversion, that problem is going to carry all the way through your signal chain. So very important to get that right. But now we are essentially entering the digital domain post that A to D conversion. In the digital domain, inside of Q-SYS, we process the signal as digital audio, where the gain adjustments are handled numerically at this point. So something to keep in mind with that conversion itself too, this is kind of like your sampling reference. This is based on the Nyquist theorem that essentially states that 1/2 sample rate is that usable frequency. So, for example, like in Q-SYS, we sample at our specs say 48 kilohertz by 24. So the usable frequency range is about 24 kilohertz, half of that sample rate. And then the 24 means essentially 24 bits of amplitude depth. So just some specs for you there. But now we are in the digital domain inside of Q-SYS, so we start to refer to our signal in different terms. Let's dive in here. Okay, so this chart looks familiar. In the analog domain, we often think of terms of dBu because it is tied to that voltage, that +4 dBu nominal. Once the signal is converted to digital, the reference changes to DBFS, so decibels relative to the full scale. And an important distinction is that 0 DBFS is not a target or operating level. That is the hard ceiling where clipping occurs, right? So that's, I see Dan nodding his head. We get a lot of calls about this. Personally, when I first learned it too, it was yeah, that was my target level, and it didn't go well. So
My first time coming into Q-SYS, I was so used to other DSP manufacturers where their input meters were at, so you'd set for around 0 +4, right? And I'm like, I'm setting my mics and I'm like, I'm never given a mic like this, the
yeah,
68 dB of gain. I've used this mic in, several other platforms, and like I did my first test call, and so I was like, oh, it sounds horrible. And then I realized there's a difference between DBFS and DBU. So yeah, it's a
absolutely.
real thing. If you take one thing away from this class, it's that almost every input meter you're going to see in Q-SYS is in DBFS, and you're going to want to set it -20. But I think Eric's going to say that about 15 more times before we
Oh
get.
yeah,
So anyway,
yeah, like you said, Dan. That's if you take one thing from this class, certainly take that. You can honestly turn it off after this if you want. I don't care. But seriously, we're going to drive that in here, and I'll explain why. So the deal is with that 0 DBFS, again, that is full scale. So that is representing the absolute maximum level in the digital domain, right? So anything above that point is clipping because there's no additional digital headroom, right? So this is our new real world data that has been converted from the analog to digital domain. So you can't really add any level past that point either to the actual original audio. This is the you can just simply boost that converted audio down the line in Q-SYS, but you're not physically adding any extra, preamp gain to that. So essentially here, -20 dBFS is going to be our target level. Okay, so -20 dBFS, this is the operating level that provides practical headroom inside of Q-SYS, and it allows for, headroom being those transient peaks and spikes to your signal. So this is going to be essentially our unity gain incoming. And sorry, did we have a question, Dan? I saw something
yeah, I
pop
was
in.
just going to drop
Yeah,
in. It says it's
yeah,
from Joel Bird. So to understand, the level meters in Q-SYS reflect 0 dBFS. So the input meters, like when you're looking in an input block, and what I'll do, Joel, is I'll open a version of Q-SYS Designer up here, and we'll revisit it along the way. But essentially, your input meters go from -100. I don't know exactly off the top of my head, but actually, I think if you go to the next slide, yeah, pop to the next slide
yeah.
quick for me. There
There's
you go.
we'll get to it here in a second. So
Yeah,
this actually might answer your question, Joel. If it doesn't, we can certainly circle
yeah.
back, but I think we're going to get to
There
it
you
in a
go.
sec.
Yeah, pop it in, pop another question if this doesn't answer, but I think we're going to get there in the next slide, so it'll make
Yeah,
sense.
cool. So essentially, again, -20 dBFS is going to be kind of our unity gain inside of Q-SYS. That's our target level, right, to allow for that headroom. And then inside of Q-SYS, so actually, I think this might address your question, but the scale is essentially -100 up to that 0 dBFS. So in that -100 is essentially muted. There's really not, audio coming through at that point. So um, another part before we move on, this is just kind of a high level, but that impacts the quality of that A to D conversion is the power supply. So something to keep in mind, that the analog to digital conversion is not just defined by the bit depth or the sample rate itself. It's analog front end and power supply. The design influences that also, the dynamic range, the noise floor, and the overall audio quality. So a lower power converter design may provide less usable dynamic range than a higher power converter with a stronger analog or power supply design. So something to keep in mind before we keep rolling here. But now we are jumping into the Q-SYS realm, right? So basically what we're going to do here, you know that we are inside of Q-SYS. This looks familiar, I'm sure, to most of you, but this is an input block. So we are showing these levels converted to DBFS, right? So that's how we're metering here. So this is showing you essentially what has been converted from analog to digital. So the really important part here, again, maybe the second most important thing, might be the most important thing again, is to make sure that all of your input levels are set to that target level of roughly negative 20 dBFS. Okay. So a way to kind of do this, because some of you, I'm sure, have used this before, but this is showing a true representation in real time of that signal level. So what I like to do, and I'll show it in a minute maybe, but they're in the physical input block itself inside of Q-SYS, where you do your wiring through your schematic. A really cool trick is you can drop in metering, right? So drop it at like a DBFS level, and you can tag the peak hold meter inside of that level. So essentially, it kind of gives you a representation of this, but it's more where it will draw. Let me get my pen here, but it will show the actual point where the signal has peaked. So you have a better representation of where you're hitting as opposed to trying to match this at all times. So it's kind of cool. It's a good little trick to use. But something to point out, why you see the word analog here, but we don't really show um, analog signal inside of Q-SYS because of the way that you have to meter the signal in a DSP is essentially you have an extra part to your analog circuit, and you take voltage off of a mic pre or post preamp prior to that A to D conversion, and then you run it through a resistor chain so you can measure how much voltage is in the system. And when you do this, some of the voltage is taken away from that A to D conversion. So it was a decision by our engineers back when they were making the Core 110F to not really sacrifice that voltage on the preamp side. So we did all the metering on the digital side. So once it has been converted, you can see the actual digital input post conversion. So this is kind of why we have no metering on analog metering on the input side, but you'll notice we'll get to it in a few minutes. On the output side, we do have that analog metering back, so you can match your decibel, your dB level for the downstream devices that they need to see. So again, this is a really, really, really crucial part of system setup and optimization. You really want to spend some time here. You want to make sure that all of your input levels are set to that target level of negative 20 dBFS. I kid, trust me, it's worth the extra time to sit here and make sure that everything is set up properly. And when you're doing this too, kind of a knee-jerk reaction, let's say you dialing your input gain in and you have your amplifiers and your downstream devices open, unmuted. Kind of best practice, and we'll talk about this in a minute, but I like to mute all of that downstream. That way, like your knee-jerk reaction isn't to, if you open this up and it's super loud downstream, you're not going to adjust this gain right here. You're not going to adjust your preamp gain. You want to set this with things muted so that you're not blasting the system. Go methodically through this and then adjust your output levels later so that you're not going to manipulate this just as a knee jerk. So anyways, that's just some tips from, trust me, past experience. So anyways, so now we're going to kind of talk about our microphones themselves. So when we introduce mics into the system, you have to keep in mind that when the microphones are open, they're coming in, we've gained them up. They're going to introduce ambient noise into Q-SYS essentially. So it's bringing that analog or just that acoustic energy into Q-SYS itself. So we basically need to make sure that the signal level of each talker is going to be above the noise floor enough to ensure speech intelligibility. So that's where you can kind of point to the AVIXA standard for speech intelligibility. I believe it's 15 dB. So it's a good starting place. But again, you want to make sure you've achieved nominal level. Everything's coming in at that negative 20 dBFS. And then a good thing to do, again, is to meter that, make sure it's legit, have someone speak into the mic, help you out so you can adjust these levels and you can focus, have a partner with you. And then you want to make sure that SNR is at least 15 dB above when the microphone is open. So when you're doing that, if the microphone isn't intelligible, if it's not meeting those specs, there's no way to fix that inside the DSP. I mean, there's some tricks you can do in AEC a little bit, cutting out some noise, but that's more for like mechanical noise, like things that are really persistent in the system, not so much just taps and clicks and things like that. So really, it's important that you make sure the mics are intelligible, or AEC won't work properly either. So there's kind of a huge, it can be very destructive if you don't spend time with that. And again, just poor SNR must be addressed at the source to maintain the integrity of that signal. So you're only really making the signal louder by increasing the amplitude of the signal digitally. Cool. So moving on, when you're setting the mic gains, the way to test, again, have someone speak, talk into the mic, and then adjust your preamp gain, set that, have the talker stop talking, and then check that peak input level when the talker is silent, and it should be -30, -35 DBFS or lower. And you notice here we have -31. So if that signal is greater than -35 DBFS when the talker is silent, the minimum SNR of 15 dB has not been achieved, which means intelligibility cannot be ensured. And keep in mind, if you increase that preamp gain to make the mic signal louder, you're increasing the noise. So it's kind of a losing battle. So this is where you really want to address your microphone source and your microphone selection itself. Maybe you could look at your polarity pattern on the microphones, cardioid, hypercardioid, where they're aimed, where they're facing. And really a big one too nowadays is with ceiling microphones, right? So in like a Shure or like Sennheiser, you can go in and you can adjust those microphone lobes. So this is where you want to kind of set up some like blocking zones where it's not going to like pick up from an HVAC or like a rack in the space. You can really set those zones and dial those lobes in so that they are kind of focused really where you want people to be picked up in speech heard from. So that's kind of a cool trick that really does help too. So again, that poor SNR needs to be addressed at the source. So if the talker stops talking in this situation and the peak level is below -35 DBFS, then we've achieved that SNR and we can keep on moving down our system. So let's say we did that. And then, again, decreasing below that 15 dB minimum SNR will ensure intelligibility, meets a functional level. And then, again, it's very difficult to make noisy signals sound good. So make sure you address that at the source if you can. So cool. Again, very important. Spend some time here. Ensure all your input levels are nominal. You're getting proper SNR. And then let's move down the signal chain here.
Yeah, and I just want to chime in there. You're gonna speak into this microphone in a normal voice and all that. You're gonna set the gain for right around -20, right? A little above. I like the idea of adding a meter after the fact, and setting the peak holds there so you can kind of tell, because it's where am I averaging this? But you can't just turn the gain down. Like if you've set the proper gain on the mic, and then when no one's talking, which doesn't happen a lot with me, if it's above that -35, I mean, you're going to have to address that room somehow with a treatment or something like that. But let's move on. But big key elements. If we don't get this input stuff right, the rest of this conversation is irrelevant.
Totally. That's a great point, Dan. So let's say we nailed that. We got everything right, sounding good, looking like decent levels coming in. What do we want to do next? Well, realistically, we're going to do some mic EQ. And I'm going to kind of caveat this where, like, again, we talked about having the system muted downstream. So like depends on where in your process you want to do this, but it's good to maybe kind of preset some levels too, but we'll just kind of talk about the blocks and then, do with it with what works best with your workflow. But with that being said, the high pass filter, essentially what we're doing here is takes everything above frequency and passes it and removes anything lower. Pretty straightforward. With like, handheld or lavalier mics in a reinforced system, good place to start is roughly 100 to 120 hertz. And you can kind of tailor from there based on the room itself. Ceiling microphones, you can go up to like 200 hertz if you care to kind of filter out some of that mechanical and background noise. Totally up to you on what sounds best there. There's no hard rule. But again, if you don't have that SNR, you can kind of maybe roll off some of the low end with the high pass, but it's still best practice to address that at the source. Next is the parametric EQ, and that's essentially, taking frequency bands and dipping those out in small, small cues across the frequency spectrum. Um, and the best practice here for sure is to cut frequencies. You do not want to really boost frequencies. That can be kind of destructive. That's more like a studio thing. You don't really want to do that in an installation space per se. But it's up to you. There's no law against it. But the last but not least is the low pass filter. So essentially that's going to roll off, your high frequencies, allow the lower frequencies to pass. Good place you can kind of set this for, again, in a reinforced system for like human speech is like 16K, maybe down to 8K. Wouldn't go too much further from there, but it can kind of help cut out some of those high-end consonants, your S's and T's that are reflective in a space. So something to keep in mind. Next, kind of diving into the parametric EQ a little bit. And a good starting spot is to, when you're initially setting up your system, building the file, or looking at your microphones that you're using, and then read the manufacturer specs that they recommend, EQ wise for their microphone, and possibly add those in early on in the process. And then when you actually go to like listen to your space, you can make those EQ adjustments based on what you're hearing in the room itself. And a good place to start is flat, keeping that parametric EQ as flat as possible so you get the natural sound of the voice. But if you need to cut some stuff out, you can start around like maybe 250 to 1K. Those are for like some of your vowels if you need to. But you want to be careful because that is like the chest and kind of the really kind of the body to your voice. So you don't want that to sound too thin. You can maybe cut out some of your consonants, 1.5 up to 6K. But you need to be careful here as well because a lot of intelligibility cuts through at those levels as well, or those frequencies. So, and last but not least, your sibilants, your kind of your S's and T's, you can cut those out mostly kind of like in like, again, like larger reinforced systems with reinforcement microphones or, voice lift. They kind of start to take off in those spaces. So you can cut those out because, but again, be careful because, in an installation, you might have like, let's say your higher education or really anywhere with CEOs and such, but their voice varies so much from person to person. So you really don't want to color this EQ too much because you might lose some of that intelligibility and some of that characteristics of their natural voice. So, and again, you don't really need to have these in any particular order per se. It's probably best practice to have the high pass filter first. That way you're not trying to make up for the lack of a high pass filter with the parametric EQ. You can kind of roll off some of that low end first and then make your adjustments to each band in the parametric if needed. So with that being said, let's jump into kind of listening to the system, right? So we have our basic EQ set, and now we're going to want to kind of address the space itself. What does it sound like? Well, we all know, doesn't matter what space you set up, at some point you're going to hear feedback, right? So that could be your levels, that could be just an interesting frequency in the mix itself. But what we're going to want to do here, we're going to introduce a tool called the notch feedback controller. And again, this is a tool. This isn't something that I would recommend like permanently leaving in your file, but it's a really cool, like helpful safety blanket if you need it. But what it's doing essentially is it's listening to the frequencies in the space. And when they exceed a certain amplitude, it's using a notch filter to cut those out kind of dynamically. So this also assumes you have like live mics in a space, right? And room speakers. But it's no real fancy measurement microphone needed. You just use a microphone that's open in the room. So a lapel mic, a handheld mic, whatever your setup looks like. So let's dive into this. And real quick, I'll caveat with we're going to go into it a little bit today. But if you really want to deep dive into this, we have some quick start tutorials on our website and through YouTube that you can find that really show you how to optimize this and adjust it accordingly for your system. So I'll talk about it, but I do no justice. They do a great job in those tutorials speaking about this. So let's look at some of the controls, some of the things you can do. So first of all, we're going to look at this kind of this axis here. So our x-axis, essentially what this is our threshold. So this is a user definable threshold. Right now it's set to -40 dB. And what that's going to allow is basically when the amplitude goes past, the frequencies go past this threshold is when the filter takes place. So pretty straightforward there. And then what we're looking at here, you notice your y-axis it's kind of creating a window, if you will, into the frequency spectrum. But basically what we're looking at is the minimum dynamic frequency and the maximum dynamic frequency. So what that's telling us is we're starting at 80 hertz here, and then we're going up to 20K. I personally would maybe, close this window a little bit so you're not, it's not as processor intensive, and you're kind of dialing it into maybe the real problematic frequencies. If you're having issues all the way across the board, you might need to do some further adjustments, but kind of find really that sweet spot where you need an extra helping hand. From there, we're going to look at our dynamic filters. So these are going to be our blue filters. We have that filter count set to 4. And you'll notice these little triangles here. These are the dynamic filters. And what that's doing is it's exactly what it says. It's dynamically filtering out those extra peaks and spikes in the frequency spectrum. So you could adjust these. I covered it up, but this is essentially the time, the reclaim time. It's 30 seconds here. And what that's doing is it dips for 30 seconds, and then it will slowly release itself back to 0. And it's taking huge notches out. So, you do need to be careful with this. And that's kind of why we like to set the dynamic filter count. We don't necessarily want to set the fixed filter count, which are orange. We don't have any in this current snapshot, but those are a little more destructive in the sense of they're fixed, right? They're not dynamic. They're not going to reclaim themselves. That frequency is permanently notched up to, potentially -12. So you got to be careful there. That can really kind of color the tone of the voice and not be as helpful as it might sound. So when you're setting this up, something else to keep in mind is this is a tool to assist you when you're setting up. So like the best practice is to kind of set this up, talk into a mic. You want to watch this filter work, see what happens. And then really, we'll address this in a minute, the user gain levels, but make sure that you're adjusting this filter and checking it with the highest level that you're actually going to be sending to the system. You don't want to set and dial it in at 50% of the user control volume. You want to make sure you peg this and test it at both. So with that being said, this is a tool. You want to make sure that you're not 100% relying on it because it's very process intensive. So what I like to do is kind of make a seesaw, a balance, if you will, between the parametric EQ and this. So let's look at the next slide here. I think we talked about that. Yeah. So use the notch feedback filter in conjunction with the parametric EQ to kind of clean up the space. So what you want to do is make sure you send the signal, see what's happening, see what frequencies are taking off in the feedback filter, and then go back and essentially adjust those in your parametric EQ. So the ultimate goal is that you don't have to have the notch feedback controller in the file really doing much at all because it's very process intensive. You don't want that chugging in the background that's, taking up overall space in your core. So something good, go back and forth between the two of those and make sure that you essentially are dialing it in on the parametric EQ side. If you're still having problems, again, go back to the start and kind of maybe look at what kind of mics you're using and kind of address that signal at the source as opposed to spending a ton of time just chopping the heck out of the frequency spectrum, because that's a very common mistake. Heck, I've done it a lot too, but I've learned over the years that it doesn't really help. So anyways, moving down the line here, let's take a look at mixers. So we're going to address two kinds here. Let me my laser pointer back. Yeah, so two kinds of mixers here. We're the matrix mixer and the automatic mixer. So matrix mixer essentially is going to be one or many signals to one or many outputs, customizable in the properties of the mixer itself inside of Q-SYS. And then you can do stereo, mono, ins, outs, whatever you like. A cool thing I like to do with these mixers, essentially a lot of folks will set up their file with a ginormous, 64 by 64 matrix mixer to send all your sources to all your destinations, all your ins and outs. Kind of like to break these up personally, make some smaller mixers, do a far end mixer, a local mic mixer, a reinforcement mixer, things of that nature. So it's a little easier to kind of track and see where your signals are going when it comes to setting your cross points, which we'll get to in a second. Auto mixers, we'll dive into those, but it's kind of the same process essentially, but it allows for, it's doing this process automatically, and it allows for dynamic outputs, discrete outputs, or you can do essentially a mix out of channel one of all the microphone or signal inputs to this mixer. we'll talk about that in a second. All right, cool. So matrix mixers, again, they're customizable. You can add mono, stereo signals, ins and outs. All of your cross point knobs come when you drop this block in, they are set by default to -100, which is essentially muted. And then you can adjust these up to, I believe, +20. So a good rule of thumb before you ever deploy a file, it'll save you a ton of time on site is to, go into emulate mode, set these levels to Unity, to 0, or to whatever you feel comfortable with for the downstream device. But something really important here is if you have a bunch of mixers in your file, I would really, really designate like one mixer, possibly two, for your overall attenuation. Because if you have 4 or 5 mixers in your file and you're adjusting the attenuation at each mixer for each individual input, it gets really, really hard to track down where it's being attenuated, why, and you get hit by a bus and the technician comes in after you. Make your life easier. Just like designate one for your overall adjustments if you can, because it gets
A good way
kind
to
of
explain it, if we've got any control programmers that are trying to brush up on some gain structure, think about that project when you programmed it, had a matrix mixer before or a matrix switch before a matrix switch, or even a switch before a matrix switch. It's like, oh gosh, where's the problem? That's the way
yeah.
to. One other thing about matrix mixers, when I used to take support calls, like if I would open the file up and if that matrix mixer is like there's cross points at -20 and -12 and some at Unity, like this, oh my, if you did, that's a first key element that I know you didn't set input gain on the front end, right? Because most everything's going to want to keep Unity. Yeah, there's times in that cross point where I'm like, hey, I need to give it 6 more dB over here. Like if I see 3 to 6 dB sway, no big deal, but there should not be -20. Now I'm saying in a normal conferencing voice lift type environment. If you're doing some production something, you might have something like that, but just thought I'd throw that in there. So
No, Dan, that's actually a really good point too, because that's something that, again, if you set your gain structure properly on the input side, you can more or less leave everything at Unity until you're hitting your attenuation trim to the actual output device in theory. So great point. Cool. So yeah, moving down the line here, let's talk about auto mixers. So we're going to address two today. We're going to talk about the first of all the gating auto mixer, and this is a take on our kind of legacy gating mixer, but it's kind of got some advanced features here. This is predominantly used for speech reinforcement with like mini microphones open. It helps manage that essentially by gating, and it removes the signal entirely, when it's not being used. So what it's doing is it's using an adaptive threshold for gating, and essentially that's the signal. It's looking at the signal level above noise. And instead of saying any value above a certain level, it looks at all the signals coming into an auto mixer. And when one signal is louder than the average noise floor of that set of channels, then the gate opens for that microphone. So the noise floor, again, is established by looking at any of the open mics. So what we're going to talk about today, kind of a little bit here, is an acronym NOM. Not Vietnam, but it's number of open microphones, NOM. So we're going to be talking about that, and essentially you can see that section over here. But for Q-SYS conferencing, we recommend, maybe not setting so many open microphones. Maybe set this to like, 1 to 4 potentially. I think we have like 8 set right here. I think that's just proof of concept. But 1 to 4, because it gets harder to manage feedback after that. But more mics equal more gain attenuation, essentially, is the way this works. So the way that it works is the target gain of 0 dB. As you can see on the output meter here, as more mics are added, they're summed and more gain is introduced. So it reduces to keep the nominal gain closer to 0. So let's take a look at some of the controls here. So the channel, the manual control, essentially what that's doing is it is bypassing the gating mix, essentially the logic, and it's allowing that signal to pass through for like a CEO or a president or someone who's really, needs to be heard at all times. And then from there, we have our last mic on. This is really helpful in the sense of, in a conferencing environment, if you're sending these mics to the far end, it helps to have the last mic that was physically on open so that you have some comfort noise for the far end, as opposed to, if everything were to be gated, it could sound like the call dropped. So you want to make sure that you have some kind of comfort noise for them. Um, Threshold above noise, that is essentially, let's see here, how loud the signal will be before the gate opens. Your depth, how far the gate is allowed closed, and then your hold time is kind of like your sustain, how long the gate is held open. Okay, so let's take a look a little bit further at the NOM really fast. So with the NOM equation, basically, this is an 8-input mixer. The max nom is set to 4 here. So we have one open microphone, and the gain attenuation is at 0 dB. So you can see the active mic indicated by the open LED, and there's no attenuation. Now, as more mics are brought in, we logarithmically attenuate that signal. So 2 mics equals 3 dB of attenuation. Then we double the number of mics to 4. The auto mixer applies 6 dB of attenuation to maintain that constant output level. So make note that we generally don't recommend having, maybe more than 3, but if you need 4, that's fine too. But that's essentially the gating automatic mic mixer. So now let's talk about the gain sharing auto mixer. So the gain sharing auto mixer works a bit differently from the gating automatic mixer, but essentially what this is doing, it's using the Dan Dugan algorithm, which you'll find on some Yamaha consoles that had this built in. But essentially there's a set amount of gain that the mixer can provide across all the inputs. And it's kind of like a gain pool, if you will. So instead of closing gates, it's applying gain to incoming signals to get that level up to 0. So let's say you have 8 mics in the system, kind of like we have here. It's looking at each of those mics, the noise floor, and adjusting accordingly. So you have the open indicator threshold, and that's how loud the signal has to be before the gain share opens and it starts applying signal to get it up to 0 dB. Then you have let's jump to the threshold level, and essentially that is the level above which to grant a given mic some of the mixer gain. You have your rest gain, and that is essentially the attenuation applied when all the mics are below threshold. So that's, what you're seeing here. And then your depth is the attenuation when gated off. Sorry, there's the depth. And then your priority gain is a manual preferential gain to add to certain mics if you need to. So let's see. So here you can see the open indicator, triggering when folks are speaking. And a quick side note, but for programmers or anyone on the call, but this is a cool place in the properties section of really the gating mixer or the gain sharing mixer. You can expose these open pins essentially, and you can have this trigger some control logic. So, it could be kind of in the older days, trigger camera presets. We're not really necessarily doing that per se by this anymore, but you can have that trigger certain presets in the space, the room, if you need to. When someone speaks, X thing happens. So something to keep in mind. But essentially, when one talker is speaking, it applies all the available gain to the open mic as close to 0 dB as it can get. And then as more people talk, less gain is available in the gain pool itself. Cool. So that was quick, but high level gating mic mixers are more for ceiling microphones or lots of potentially open microphones. It's better for like larger gain management. And then gain sharing, better for a few open mics like Q&A, where you just have a panel. It's a little bit quicker to react, and you can have those mics kind of open, just kind of sharing the gain amongst themselves. But it really depends on what you need for your system. All right, so moving down the line here, putting it all together. Notice really quick, we're running through the signal chain here. I'm going to make a quick note about user gain controls. So your user control, your program, you kind of want pre-mixer. And then for your mics, you want that post-auto mixer. So it's adjusting that mixed level as opposed to sending different levels to the mixer itself. It's taking that single output and adjusting it accordingly. So just a quick note. Okay, so there are a few other options to adjust mic levels automatically in the Q-SYS file. So you can use a compressor, or you can use automatic gain control, which is AGC for short. The compressor is user definable. It helps with multiple people speaking into the same gooseneck mic, for instance. Like if you were at a podium, you could set a compressor to that gooseneck mic so that when someone comes up to speak who's naturally louder, it kind of throttles that voice back, compresses it. And then the next person, it's not going to essentially hit that threshold, so it's not going to compress. So it's a good way to kind of help limit your system a bit, almost like a, kind of like really just throttling it back essentially. And then for AGC, the automatic gain control, if you need some gain back automatically, this is kind of helps for quiet talkers in space. I would say the caveat with this, it's you can use it in a reinforced system or a voice lift system, but it's best maybe for far end audio because this is applying, additive gain. So it could potentially cause some issues to your overall gain structure down the line. So something to keep in mind. All right, cool. So what is wrong with this picture here? We have gates on gates. So we essentially are double gating, which can negate. But essentially what we want to do is not put these in front of the gating mic mixer because the gating mic mixer is listening to that noise floor and it really wants to know kind of the levels and base its how it opens the mic channels based off of the noise floor itself. So if you have a gate in front, it can send false triggers or it really is not listening to the actual clean mic signal. So this can cause problems and you do not want to do this. It's just bad practice and gives you a lot of headache, I promise. So moving through here, we now are going to kind of start to dive into AEC a bit. So we didn't have that in our system earlier. I'll show you where it comes in, and we're going to talk about how to tune it a little bit and just best practices. So what we're going to look at is we have our microphone signal. Let me go back to my laser pointer. Microphone input level set. You'll notice the first thing post the microphone inputs would be the AEC block itself. We want that true raw mic data to go directly from the mics to the AEC block so that it has the best representation of that true audio signal. And then from there, you can go to your gating mix out to your far end call. And then looking at the path to the near end here, the sources potentially coming in. And basically the rule is anything that is coming out or going to the speakers in the space needs to be sent to that reference back to the AEC. So you'll notice too, we'll harp on this in a minute, but why it's so far down the signal chain, you really want that reference to be sent right before it hits the output block because you want it to have any kind of EQ gain adjustments applied to it so that it's sending the truest representation of what's about to come out of the speakers back to that AEC block. So let's dive in a little bit. Okay, so looking at AEC itself, let's talk about some terms. So latency is essentially how long it takes from the signal to make it from the left side of the AEC block to the right side of the AEC block. And AEC requires what's called look-ahead time. So that time adds latency to the overall signal. So this is kind of our current specs about AEC, and essentially the input to conference output is roughly 32 milliseconds on these cores themselves. And then if you're using the input to reinforcement output, that's roughly 21 milliseconds. So just a quick look at this, you can see all these in our specs and our white pages. So anyways, looking next at our tail length here.
I'm going to pop in real quick.
Yeah, sure.
Hey, by the way, we just give a start time on these, and typically they're 1 hour. But this deep dive and another, there's a handful of other ones that will tend to go a little bit longer. If for some reason you can't stay attached for the rest of the hour, we do send out a recording, like I mentioned at the beginning, and you'll get all of the PowerPoint deck in PDF form as well too. So, Eric, I love where you're getting, you're deep diving into this. So, by all means, if you can stay attached, everyone, please do. If you can't, we certainly understand. No offense here. You'll still get a copy of the recording and everything else too. So, yeah. So keep on rolling, Eric.
All right, cool. Yeah, thanks, Dan. Sorry, guys, I'll try to burn through this, but again, you'll get a recording. So anyways, the tail length. So what we're looking at here is, AEC is a time window essentially. So it's capturing the room as it is in that current moment of time. So tail length it kind of looks at that window and computes how many of those reflections we're going to be able to cancel out. So the maximum is 400 milliseconds. The minimum is 100. And then out of the box, core AEC blocks come with 200 milliseconds set by default, which pairs with Sennheiser and Shure, their microphone specs. So you would change this if you had a really acoustically nasty space that has a ton of reflections, reverberations, and you really need that extra help. but this does eat into your overall AEC channel count. So you need to kind of keep that in mind and really look at the specs before you go and adjust the time of your overall tail length. So something to keep in mind, but it's definitely very process intensive on the core itself. So this is one of the more intensive blocks you can drop in, but it's certainly necessary. All right, cool. So the way that it works basically is we're going to look at an fun acronym RMLR. So that's reference to microphone level ratio. And that is, the difference in between the reference signal that we're sending to the AEC block and the resulting signal that comes out of the speakers and hits the mic itself. So, the signal flow essentially is audio comes out of the loudspeaker, bounces off all the surfaces, and then it comes back to that microphone. So these are picked up and measured by the AEC algorithm and compared to the reference value. So to send the most accurate reference value, again, you want to pick that signal directly before it comes out of Q-SYS, before it hits that loudspeaker, so that it has the truest representation of the tone of the signal itself that's coming out. And essentially, this compares both of those signals, and we get the RMLR. So, and this is a ratio, again, because it's comparing the two. And the difference between these is our echo return loss, so our ERL. But basically, this is showing us how much we need. ERL shows us how much we need to cancel out of the AEC algorithm to remove those far-end reflections. Cool. So keep trucking here. I think I'm on slide 30 out of 60. The last couple are pretty quick, so we'll keep burning. But essentially, there are a few more terms to look at. RES, residual echo. That is after we cancel out the signal. This is the special sauce that we apply to help make it sound good. So this is, everyone has their own algorithm. This is Q-SYS's at this point. And then voice lift. This is essentially mics that are in the system that are being reinforced through the speakers that are coming back, not just going to the far end. They're being lifted or reinforced in the space. Those terms are more or less interchangeable. And then mix minus. This is essentially strategically mixing the voice lift mics so that when someone speaks into a mic, that signal is being sent to all the speakers except for the closest one to the source. It's kind of challenging to set this up and can kind of be expensive if you really have to isolate each speaker zone, but it's worth it if you can do it. And then a quick note on reinforcement outputs. We are not going to dive too far into show you how to set up AEC for reinforced microphones. I'd be happy to take that offline. We can, that kind of depends per system, to be honest. So that's something myself, Dan, or any solutions architect or application engineer. So you can talk with them after if you'd like to discuss your particular use case. Okay, so again, the conferencing signal flow to the far end. What we need to do, we have our mics in, AEC block, gating mixer, and then again, we're sending any signal that is going to the local system back to the AEC reference block here. Okay, all program sources, all far-end conferencing need to be sent back to that block. Cool. And then this is something that's very important. We are showing you what not to do here. So you do not want to put any kind of processing prior or pre the AEC block. You want the AEC block to have the truest representation of the input signal from those mics itself so it can listen to the actual real-time data from the mics. You can certainly put this post, and I highly recommend it, but I would not put this pre-AEC block. And this is a good time too, if you had like multiple paths for far-end conferencing, you can maybe set up a smaller, another AEC block, send maybe the same or a different reference to it, but have different processing to those output channels, depending on where it's going or what the setup is in the system. Okay. Again, really important to make sure that you're sending the correct reference. So your program sources need to go to the reference, anything that's coming out of the speaker, so that the far end doesn't hear it twice. So this reference point we find is unfortunately wrong a lot of times, and this causes a ton of issues in the system. So you really want to make sure you spend time getting this correct. And then again, if you do have reinforced mics in the system, never send that microphone signal back to itself because it gives you that kind of underwater sound, which I'm sure some of you have heard at some point. So anyways, next step, this is going to be kind of where we actually start to address our output signal into the system itself. So what we're going to do is we want to kind of start to focus on our gain staging here. We're going to get deeper into the weeds in a minute about the actual levels, but what we're going to do is to set this up in a way that we have our input signals. They're all coming in at -20 DBFS. We're making sure that's a thing, even from our far end. When the far end speaker talks, that's coming in correctly. And then from here, I like to bring in like a consistent source like peak noise or like someone who's consistently talking on the far side so you can get a good representation of what the levels look like. And then from there, bring up your amp levels. So good level coming in, slowly bring up your amp levels to your desired SPL, maybe like, for a conference room, 70 to 80 dB SPL. Totally depends. There's no 100% specs on that, depending on what your client wants to see is really the right answer. So from there, if you're downstream amp, yeah, sorry.
Oh, Martin says in the question section, you may want to mention double AEC with a codec and where that is. I know personally in my experience, like back in the hard codec days, like you would want to disable the AEC in that hard base codec and not be doing it twice. And I don't know how many people are installing it. I'm going to really date myself and say Tandberg. That was even
Yeah.
Cisco buying them. But I found that, and this is my experience, and I'm not out there dialing in conference rooms, but I found that, there is some AEC that's built into Teams and Zoom and all of that. We still want to do AEC on the DSP side because it's going to be unique for each microphone and the room scenario and all of things like that. But definitely in the older codecs and stuff like that is where I would typically see that. So just wanted to
Yeah,
that.
that's a really good point, Dan. And that's, kind of the best, practice is to do it in Q-SYS if you can. There's some interesting scenarios if you like, again, I'd be happy to talk offline about this. It's kind of a per system basis, but with intelligent mics these days, beamforming mics, there's some AEC happening there too.
Yep.
So it again, be happy to talk on a system by system basis on that, but best practice is to do it inside of QSYS, is what we recommend.
Yeah,
So
or I mean, we try to make this a gender or a brand neutral
yeah,
version. I mean, if you're using a DSP, usually that's the best place, and
yeah,
because it
good
can be
point.
done per mic. But we'll roll on. So yeah.
Yeah, no, great point. So so we have our output level set, our room, we're getting our desired SPL level. Now we can start to do some testing, right? So what we're going to do is start to do some checks with our conference room. So what we want to do, make sure that input level's coming in properly. We're going to do a test call. So this is where you can kind of make sure your levels are set and your EQ maybe sounds good. We'll dive into that in a second. But what we like to do is you want to start making some tweaks if you need to make sure that your things sound good on the far end. And what I recommend to do is, make sure that if you're programming the space itself, set in the room and listen, and then also go down the hall and join a call so that you can hear what's happening too, so that you're hearing both sides of the story as opposed to relying on, probably a valuable technician, but you can actually physically hear it too, to make sure that there's no issues. So essentially, if you need to add in some noise reduction, you can. That's totally cool. This goes from 0 to 20. This is going to cut out some of those steady HVAC noises and really just those, static background noises. And I believe it's disabled by default, so you can enable it if you need it. And then we're looking here. So this is kind of where we're going to be able to tell how the system is performing, how the AEC is actually working. So with RMLR, you essentially want this to be dead center when the far end is speaking. You want this to be targeted around that green color, right? So, and again, you want to listen on both ends, give decent level into the system so you can see how this is operating. You need to adjust your reference gain you're sending to make sure this hits that target level. You can do so with the reference gain knob here, or fader rather. And then if you need to use your adaptive filter, you can do that. Essentially what that's doing is I would only really use this if you have mics pre the AEC that are like push to talk, so they're muted, and then when they open, the AEC has to catch up. So what this does, this pauses the convergence and adds in noise to the AEC to hold it there, so it doesn't have as far to go when it catches up. And you can do this again with the reference level if that's below. Okay, so with the post processing, we have residual echo suppression down here. And what that's doing is essentially it's typically always enabled, but you can adjust if you really need to cut out some extra echo. But this is where you're going to potentially introduce half duplex. So you want to have like, both you and the far end speaking at the same time to make sure that it's not cutting out your one of the other's voice. So make sure you can have a fluent conversation back and forth. Okay, moving down the line. Again, you want to test for that double talk. You can adjust this with the RES, but you really want to make sure you, like I said, have that conversation back and forth, speak directly to each other, make sure you can hear each other, and adjust there accordingly from both locally and on the far side. All right, so what if you still have echo? Well, this is a good place to, utilize some troubleshooting skills, go through and use some of the tools that are built in. With Q-SYS, we have a hover monitor, so you can like listen to that AEC reference signal you're sending. You can directly listen to that pre-AEC block to make sure you're sending the correct reference, make sure your levels are set appropriately, check your wiring path. I like to mute all of the microphones if you need to. And then you can slowly open up each microphone one at a time and see which one is maybe having the echo introduced over that open microphone. Cool. And if there's still echo, this is when you might need to have a come to Jesus moment and look at the size of your core. If you want to adjust that, initial 200 milliseconds up to 300, 400 milliseconds, 300 or 400 milliseconds. Or if you want to address, the reflectivity of the space. If this is like a glass, walled, hard surface floor, maybe at a carpet, maybe at a rug, that could be potentially cheaper than beefing your DSP or your core up to a larger model to be able to allow for more AEC channels if you have to boost this 300 to 400 milliseconds. So it can be a tough call, but totally up to you. Lastly, just make sure you're testing everything, go through each instance of the AEC, make sure you repeat this on any potential scenario that might come up. So cool. After the mix, there's a couple of things we can do here. We're going to talk about some EQ level controls, limiting and delay. So let's dive into those. Next, when you are setting up your file, honestly, initially, what you can do is look at your speaker. If you're using, for some other reason, a speaker that is not a Q-SYS speaker, you can look at the manufacturer's recommended EQ settings and go ahead and dial those into a speaker block. You can also save those for later file deployment too. And then from there, if you're using the Q-SYS speaker, those have the intrinsic correction built in. So you can drop that in and it already kind of has the shape that we recommend. Lastly, when you're pushing audio through the room, you can look at your room's EQ curves. This is when you're going to walk around and you want to, check the response of the room itself. You want to go and kind of, try each spot at the table, stand under these speakers, make sure that you're getting as flat of a response as possible or whatever you'd like to hear in the space. Then you can start EQing some of your output levels. And, check for speaker taps. Make sure that your speakers are tapped correctly. I've seen a lot of times, but someone will install these and one set to 8 ohm, one set to 7.5 watts. So really make sure that everything's uniform in the system to the best of your specs that you'd like to see. Okay. Next is user gain controls. And I would highly recommend to give as little control as possible here. This is totally up to you in the sense of, this can be pretty destructive on the downstream devices. So for instance, a lot of times I've seen, someone will drop in a user control block for the microphone level, right? So if someone has a far end beamforming mic coming into the system and the far end can't hear it very well, somebody will add in a gain adjustment. But how many times have you been on a call with someone and one person out of the group says, hey, it doesn't sound very good, but the other folks are like, I can hear it pretty well. Well, you don't know what speakers they're listening to or headphones. So if you start adjusting that output level, you could clip and make it sound pretty poorly for everyone downstream. So
I always use the rule of thumb, never give people a volume knob to something they can't hear, right? So if I'm hosting that or that call and I turn my outbound volume up, I don't know what's right. So it's, it needs to be addressed on the other end. I want to just jump in real quick back here. Sure. We had a question come in, question statement, whatever. That was, does a scaling license on a Core 8 Flex or Core Nano give you more AEC? And it doesn't. The AEC channels are going to be 8 for each of those platforms. What the scaling license does in those is it updates the number of network audio channels that you can have from 64 by 64 to 128 by 128. Network audio streams from 32 by 32 to 64. And so that's kind of, it's just a more processing power and a little bit more streams that you can handle in and out. So just wanted to kind of dispel that. I think that question comes up a lot. Like, well, I bought the upgrade license for the Nano. It doesn't add additional processing to be able to facilitate more AEC. So
Cool. So
let's
let
roll
me,
back in. Thank you.
yeah, you're good. No worries. Thanks, Dan. So looking here, um, if you do need to add user gain controls there, it's totally acceptable, obviously, for microphones, like reinforced mics in the space or maybe program level. But by default, when you drop in one of these gain blocks, the max gain and min gain is, I believe, -100 up to plus 20 dB, which is a huge level variance. So what we recommend is to come in and maybe change this max gain and this min gain. To the end user, it still just looks like a fader, a slider, whatever is forward facing on the UCI. They have no idea really how far that range is, but it's going to ensure that you're not clipping downstream devices when they adjust that. So another good rule of thumb is to, when you do set this, make sure that you are testing your system at kind of 50%, like your starting place, and then also with the system pegged at this highest max gain that you're going to give the user, so that you can ensure that nothing is clipping downstream. It sounds good, nothing's feeding back. So definitely check those levels there. Okay. Something you can do though to help protect, you can add in a peak limiter. Essentially what this is doing, it's protecting your downstream devices by acting as a brick wall limiter essentially. So this is a really important thing to add in to protect your downstream devices and your amplifiers. So you look at this, basically it comes default at 0. So from here, it's still possible to clip and go beyond this point. So, looking at the signal here, it is truly passing that. So what we like to do is to add in maybe a 3 dB. Really just look at the downstream device specs and levels and make sure that you're setting this so that it's not going to clip those. So just protect them at all costs, because this can certainly be a detriment to your system. All right, cool. If you are using Q-SYS QLAN amplifiers, we do have limiting built in. So we have AC limiting, which is peak limiting of the input signal, essentially. And then your protect limiting, that is essentially thermal limiting, looking at transformers, which are looking for the impedance mismatch. And then compute limiting, for some reason, if your load type is straining the amp too much, it will limit. Okay. And then finally, we need to start looking at converting this back to analog, right? To microline level to hit our output devices. So RMS output level for line outputs, you notice here, it's plus 21 dB by default, dBu by default. And then you want to check here your sensitivity that is required and requested of your downstream devices, so that you can make sure that you match this sensitivity level to that device. So, keep in mind that, professional line level audio is plus 24 dBu, but consumer level is -10. So you want to make sure you adjust that accordingly. And this kind of looks at the output of I believe, a Core 110F. And then the max RMS output level specified is plus 21 dBu. Our peak output level is at plus 24 dBu. And then accounting for the 20 dB of headroom in our signal, that puts us at plus 4 dBu nominal level, aka professional line level. And then, what if we need to scale that output for a consumer level device? This is where you would decrease that output gain, as you see here. And this doesn't manipulate the digital gain here, which is still being measured in DBFS. So again, make sure that your proper gain structure, and you want all the components in the chain to be able to see that the level that they are requesting, right? So you're not clipping anything downstream. Okay. Again, work with your customer. Make sure you know what levels are expected for all downstream devices and adjust accordingly. If it's mic level or if it's line level, test the space to ensure that all levels are coming through at any level variation, that they're not going to clip or peg anything downstream. So be careful there. Make sure your levels are happy, they're healthy. And then lastly here, the just a quick note that the noise floor is at a fixed level at the output. So this means that your SNR is much smaller when the signal is at microphone level, right? Than it would be if it were at pro line level. So if gain is added to the downstream device, it does increase that noise floor. So make sure that when possible, you are using professional line level to get the best signal to noise ratio. Okay, cool. Quick recap, and then we'll get out of here. So basically, input calibration. This is your gain staging. Incredibly important. Make sure this is set no matter what. You're to the best practices that we talked about today. From here, make some mic EQs based on the manufacturer's specs, whatever sounds good in the space. Don't rely too heavily on the notch feedback controller. Do as much as you can with the parametric, but tastefully. Next, the dynamic microphones, use auto gain control, compression, anything that you can use to help you, especially in an installed system, so that when you walk away, nothing is going to be clipped. Everything's going to sound pretty good overall and mixed well. And then next, we have auto mixing. So, again, it helps with multiple mics in your system. And then lastly, the user gain, we want to make sure that this is set to as little gain control as possible. And then limit your outputs and calibrate your outputs to what the downstream devices need to see. And Dan, I think that's it, man.
Yeah, one thing about that last point of, a lot of people, I used to always set my rooms for negatives or for 65 dB of output. And you don't have to get crazy. Like just download a free like DB app or something for your phone, set it on the table and, play a calibrated source into the room. And I used to always set them for 65. And then I here, I think it says 70. And I noticed that whenever someone would sit down in one of my conference rooms, first thing they would do when the meeting started was go tap, tap. The reason I chose 65 was like, that's the human voice. The average human voice speaking at, given distance is about 65 dB. But in a conference, our brain wants to hear that voice coming from the far end, just a few dB louder than normal. So that's kind of why the 70. I always like to throw the science around it sometimes, or the psychology of it too. So, but yeah, great presentation. Really a true deep dive here, Eric. I love your preparation and I love your sharing and knowledge on this. Also, that last slide again there, you will get, if you go one more, yeah, you will get, I call this the placemat. It's, if you print it out on 11 by 17, it's a really nice guide that walks through everything that he's talked about here. There's one side that is gain structure, and then you can double print it, or you can make 2 pages of it. But it's a nice, you'll get that in PDF form, and basically it summarizes this last hour and 15 minutes up in 2 different really easy to use guides. So it'll look a little different than this because the marketing teams updated the branding on it, whatever, but still the same content and info. So I think we kind of handled all of our questions along the way, which is good because then, we're not talking about, and someone's not asking a question about 24 slides back or something. So, but we really appreciate the dedication of time. I think we only had, a handful of people that needed to drop off. This is a great thing. We host this quarterly, and we always get attendance. Like there's people that just, hey, want to get a refresher. There's nothing really that changes in this science. So, but it is one of the things that if you've got younger or new to the business technicians and people that are going to be out calibrating systems, get them signed up for this. Give them the video link to watch, or whatever the case may be. But gain structure is probably one of the biggest challenges that we see in our support calls, that deal with audio. So, Eric, any closing thoughts?
No, Dan, I mean, that's seriously, you hit the nail on the head. That, like, for myself, learning Q-SYS back, however many years now, but trying to set this correctly, it immediately got rid of, I'd say, 50% of the issues I was facing. So I highly recommend, to spend some time here. It can't miss. This is incredibly important. So yeah, feel free to go back and watch this and reach out to myself or any other, engineers that would be more than happy to deep dive with you if there's something we missed here. So yeah.
Victor Poon jumps in and says, thanks so much for the presentation. Timing's good. I just finished up setting conference. now I need to go fine tune them with what you learned. And that's exactly right. You're going to find that, man, there was that one room that was, I really struggled with and whatever. And you're probably going to go in there and find, oh, shoot, two of the beams on the ceiling mic or whatever, had the wrong gain on them or who knows what. So there's lots of variables. This isn't going to solve everything. I appreciate it, Chris. But these are things based in science that don't change and all of that. So everybody have a great day and get on with the rest of your week, and we'll see you for the next deep dives that we've got set up. So let me see. Well, I do know we've got coming up on September 8th, planning clocking domains. So when you're dealing with the digital world, and digital audio, clocking is paramount, and how that works. You throw one core in a system, probably no big deal. All of a sudden you start tying more to a network. There's going to be things that you need to think about there. That's another one that we try to run quarterly or semi-annually. We're also going to have on the 15th, introduction to our NVM series. So if you've used our NV series of video products and thought, man, I wish there was a lower cost version of this for bigger deployments and all of that. Well, we're here with that product. If you've missed that product announcement, it's out there. This is going to be just an introduction to what those products are and how they can do, and touch on a little bit of the cool features and functionalities that we've added, with this product line to be able to deploy on mass scale. Think about doing big convention centers, doing sports bars, things like that. And then I just shoved this one into the order of precedence, is demystifying global versus local scoping. I don't know what that means because I'm not a control programmer, but Jeff knows, and Jeff Perkins knows. He's the guy that writes all of our control coding. He's the guy with the bow tie. So he's going to be premiering his latest control quick start. So if you're a Lua programmer or you got Lua programmers in there, he's going to talk about the nuances of demystifying global versus local scoping inside of there. And then at the end of September, we're going to have a how to choose the right Q-SYS core processor. Several months back, we released the Core 24F, the X10, a lot of those new cores. And we just want to make sure people kind of understand, hey, if you were doing Core 110s, this might be your next solution. Kind of give you an apples to apples of what the new processors are and how to replace them. So with that, everybody have a great day. We appreciate it.
Yeah, cool. See you guys. Cheers.
Yeah.